Stimuli-responsive smart polymer materials, mechanisms, synthesis, and applications. Stimuli-responsive polymers, often referred to as smart polymer materials, constitute an important class of advanced functional materials that adapt their properties in response to environmental stimuli. These polymers respond to a wide range of chemical, physical, and biological stimuli, including light, temperature, pH, electric and magnetic fields, humidity, ions, enzymes, and reactive oxygen species, by altering parameters such as solubility, swelling behavior, surface energy, or molecular conformation. Such responses are often reversible and controllable, enabling applications in medicine, electronics, soft robotics, sensing, drug delivery, and industrial technologies. Recent developments in polymer synthesis and molecular design have enabled the creation of multi-stimuli-responsive systems with enhanced functionality and adaptability. This report reviews the synthesis, classification, mechanisms, and applications of stimuli-responsive smart polymers, highlighting their role in emerging technologies and advanced materials engineering. Smart materials have become essential components of modern science and technology, with applications in medicine, electronics, soft robotics, chemical processing, and automotive engineering. Among these materials, stimuli-responsive polymers are particularly promising because of their ability to respond dynamically to environmental signals. The concept of smartness in polymeric materials can be compared to biological intelligence. Just as living organisms recognize and respond to changes in their environment, smart polymers detect external stimuli and respond through structural or physiochemical transformations. These responses may manifest as changes in solubility, swelling, hydrophilicity, hydrophobicity, micellization, or mechanical behavior. External triggers for these responses may include physical factors, light, temperature, pressure, electric fields, chemical stimuli, pH, ions, redox conditions, or biological signals, enzymes, glucose, microorganisms, and viruses. In many systems, the response is reversible, allowing the polymer to return to its initial state once the stimulus is removed. Increasingly, researchers are developing multi-stimuli-responsive polymers capable of responding to multiple environmental signals simultaneously. Synthesis and classification of stimuli-responsive polymers. Polymerization methods. Smart polymer materials are commonly synthesized using radical polymerization techniques. Two major categories are used: conventional radical polymerization. This method operates under relatively mild reaction conditions and can accommodate a wide range of monomers. It is widely used in industrial polymer synthesis. Controlled radical polymerization. Advanced techniques provide greater control over polymer architecture, molecular weight, and functionality. Important methods include reversible addition fragmentation chain transfer, RAFT, polymerization. Atom transfer radical polymerization, ATRP. These techniques enable precise incorporation of functional groups responsible for stimulus responsiveness. Classification based on physical form. Stimuli-responsive polymers can exist in several physical forms, including hydrogels, polymer solutions, micellar assemblies, self-organized clusters, surface coatings, solid polymer networks. Each form provides different mechanical and functional properties suitable for various technological applications. Functional classification. Based on operational mechanisms, smart polymer materials can be grouped into shape memory polymers, SMPs, self-healing polymers. Responsive hydrogels. Actuating polymers. These materials can change shape, repair structural damage, or respond dynamically to environmental signals. Physical stimuli-responsive polymers. Light-responsive polymers. Light-responsive polymers are among the most extensively studied smart materials because light provides a non-invasive, controllable stimulus with high spatial and temporal precision. These polymers often display biocompatibility, water solubility, and biodegradability. Two primary mechanisms are used in their design: photocleavage. Photocleavage involves light-induced bond breaking that produces new chemical species with altered physical properties. Photochromism. Photochromic systems undergo reversible structural changes such as cis-trans isomerization, intramolecular rearrangements, or pericyclic reactions. Common chromophores used in these systems include azobenzene stilbene and cyanostilbene dialethene spiropyran hydrazone coumarin. For biomedical applications, visible light-responsive systems are preferred because ultraviolet radiation may damage biological tissues. One well-studied photolabile group is O-nitrobenzyl alcohol, which undergoes photo-rearrangement under UV irradiation, 300 to 365 nanometers. Near-infrared, NIR, responsive polymers have also gained importance in photothermal therapy, PTT, where localized heating can destroy infected or cancerous cells while simultaneously triggering drug release from polymer matrices. Temperature-responsive polymers. Temperature-responsive polymers alter their properties, particularly solubility, in response to heating or cooling. These systems often undergo reversible transitions between sol and gel states. Key parameters governing these transitions include lower critical solution temperature, LCST, the maximum temperature at which a polymer remains soluble. Above this temperature, phase separation occurs. Upper critical solution temperature, UCST, the temperature above which the polymer becomes soluble, forming a single phase. Common temperature-responsive polymers include poly, N-isopropylacrylamide, PNE-PALM, poloxamers prolastine. Hydrophobic groups such as methyl, ethyl, and propyl substituents often contribute to temperature-sensitive behavior. Electric field-responsive polymers. Electro-responsive polymers change their physical or mechanical properties in response to electrical stimuli. These systems convert electrical energy into mechanical motion or chemical changes. Two major classes exist. Ionic electroactive polymers, EAPs. These materials rely on ion migration and concentration changes within the polymer matrix. They operate at low voltages but often exhibit slower response times. Dielectric electroactive polymers. These polymers respond through electrostatic forces between electrodes and display rapid actuation but require higher voltages. Common electro-responsive polymers include polypyrrole polyaniline, PEDOT, poly, 3,4-ethylene dioxythiophene, and chitosan. Applications include soft robotics, drug delivery systems, electrochromic devices, actuators, and conductive scaffolds for tissue engineering. Magnetic field-responsive polymers. Magneto-responsive polymers are composite materials containing magnetic nanoparticles embedded within polymer matrices. Typical magnetic particles include magnetite, MULTIVALENTFE304, magamite, gamma iron 3 oxide. These particles are combined with polymers such as polyethylene glycol, PEG, dextran poly, vinyl alcohol, PVA, and polyethylene-imine, PE. Magnetic nanoparticles can be classified as soft magnetic, low coercivity, or hard magnetic, higher coercivity. Magnetic stimuli allow precise spatiotemporal control of polymer behavior, making these systems attractive for drug delivery, soft robotics, and biomedical imaging. Chromoactive polymers. Chromoactive polymers exhibit color changes when exposed to external stimuli. These systems are classified as photochromic materials responding to light exposure, thermochromic materials responding to temperature changes, electrochromic materials responding to electrical potentials. Such materials are widely used in smart coatings, sensors, displays, and security technologies. Ultrasound-responsive polymers. Ultrasound-responsive systems utilize mechanical vibrations generated by piezoelectric materials. Ultrasound waves are typically categorized by frequency: low frequency, less than 1 MHz, medium frequency, 1 to 5 MHz, high frequency, 5 to 10 MHz. These waves can influence polymers through thermal effects or through cavitation, where oscillating gas bubbles produce localized mechanical forces. Ultrasound-responsive polymers are particularly useful for drug delivery and biomedical applications because they allow remote activation without introducing additional chemicals into the system. Chemical stimuli-responsive polymers. pH-responsive polymers. pH-responsive polymers contain acidic or basic functional groups that can donate or accept protons depending on environmental pH. This change alters polymer charge and molecular conformation, affecting properties such as solubility and swelling. Natural pH-responsive polymers include alginates, hyaluronic acid, and chitosan. Synthetic pH-responsive polymers include polyacids and polybases containing functional groups such as amino, pyridine, or imidazole groups. Some polymers contain pH-labile linkages such as hydrazone, imine, or cis-aconitl bonds that degrade under acidic or basic conditions. Ion-responsive polymers. Ion-responsive polymers respond to variations in ionic strength or ion concentration. Changes in ionic conditions alter electrostatic interactions within the polymer network, resulting in swelling or contraction. Examples include alginate systems responsive to Ca² ions and chitosan systems responsive to Mg² ions. Redox-responsive polymers. Redox-responsive polymers undergo structural changes in response to oxidative or reductive environments. Such responses often involve cleavage or formation of redox-sensitive bonds such as disulfide linkages. Hydrogels containing disulfide bonds have been used to control the release of biomolecules such as bovine serum albumin in the presence of reducing agents like dithiopheritol, DTT, or glutathione, GSH. Water-responsive polymers. Water-responsive polymers respond to changes in humidity or water concentration by swelling or shrinking. These materials can generate mechanical energy from moisture gradients. Cellulose-based hierarchical structures are frequently used in humidity-responsive systems due to their porous morphology and high water affinity. Reactive oxygen species-responsive polymers. Reactive oxygen species, ROS, are generated in biological systems during cellular metabolism. Excess ROS can damage lipids and DNA, providing a biological trigger for responsive materials. ROS-responsive polymers often contain functional groups such as thioethers selenium or tellurium groups thioketals phenylboronic acid derivatives. These polymers degrade or change solubility in oxidative environments, making them useful for targeted drug delivery and biomedical therapies. Biological stimuli-responsive polymers. Glucose-responsive polymers. Glucose-responsive polymers are being investigated for applications in diabetes treatment. These systems detect glucose concentration and regulate the controlled release of insulin accordingly. Enzyme-responsive polymers. Enzyme-responsive polymers exploit the catalytic specificity of enzymes to trigger structural or chemical transformations. These systems are particularly useful in environments where specific enzymes are overexpressed. Advantages include high selectivity, spatio-temporal control, and enhanced permeability. However, premature activation may occur when similar enzymes are present. Multi-Stimuli-Responsive Polymer Materials. Multi-stimuli-responsive polymers are capable of responding to two or more environmental triggers simultaneously. Possible stimulus combinations include light and temperature, pH and enzyme activity, temperature and redox conditions, pH, temperature, and humidity. Designing such materials requires complex molecular engineering, often involving the incorporation of multiple functional groups within the polymer backbone. These materials exhibit enhanced versatility because different stimuli can trigger independent or sequential responses. Applications of stimuli-responsive smart polymers. Stimuli-responsive polymers are being used in numerous advanced technologies, including targeted drug delivery systems, biomedical implants and tissue engineering scaffolds, soft robotic actuators, self-healing coatings, sensors and diagnostic devices, smart textiles, environmental remediation technologies. Their ability to adapt dynamically to environmental conditions allows the development of responsive and adaptive material systems. Conclusions. Stimuli-responsive smart polymers represent an important class of adaptive materials capable of responding dynamically to environmental signals. Advances in polymer synthesis, molecular design, and functionalization have enabled the development of systems that respond to a wide range of physical, chemical, and biological stimuli. Multi-stimuli-responsive polymers offer particularly promising opportunities due to their enhanced functionality and adaptability. Continued research in this area will enable the development of advanced technologies in medicine, robotics, electronics, and environmental engineering. As societal and technological needs evolve, smart polymer materials are expected to play a central role in creating innovative solutions for modern scientific and industrial challenges.